Hello everyone, we'll start with problems on viscosity that we have solved earlier, but there is a good variety of problems over here. We'll be seeing them here. There are some things which are moving inside the fluid medium, and the velocity distribution is slightly different. So these kind of things we'll be discussing in this session. We'll go ahead. Okay, the problem reads this way. The velocity distribution near the solid wall at a section in a laminar flow is given by u is equal to 5 sine 5 pi y for y less than 0.1 meter. Compute the shear stress at different values of y. The dynamic viscosity of the fluid is 5 poise. Now look at this figure or this figure. Here there is a stationary wall. They have said that solid wall, and that is what it is. And there is a fluid which is standing above. And if you take any point at some y is the distance from the base. It is shown here. If you go some distance y, what is the velocity at that point? That is shown here. So if you go farther and farther, the velocity gets larger and larger. But after some time, you move any amount of y, this u is becoming constant, right? There is no change in velocity. But nearer to the solid surface, nearer to the stationary surface, when the fluid is moving, right, there is a change in velocity at a larger extent that you can observe here. That though the distances are shown here for just an observation, we have made points at equal intervals. But look at this. Here the distance is same, but the change in velocity, that is u was so much, now u has become so much. So this is du and this is dy. So du by dy, if you look at, this is quite larger compared to over here, because here I have kept dy same, but the change in velocity, if you look at, it is quite less. So as you move away from the solid surface, as you move away from the solid, means as y increases, the du by dy is becoming less and less. As you are nearer to the surface, the du by dy is larger and larger. That is what is the observation. Now we'll go ahead. What is given in the problem? The mu 5 poise, but we will be consistently using newtons, meters and seconds as the units. So it has to be converted into Pascal second, and then if you know that 10 poise makes 1 pascals, we divide it by 10 so that you get it in Pascal second. Now it is given u is equal to so much. U is 5 sine 5 pi y. But they are asked, calculate, compute shear stress at a distance at y something. Then shear stress, you know that it is given by du by dy, and then using du by dy, shear stress tau is equal to mu into du by. This is the shear stress equation. So that is what we are supposed to use for shear stress. So this equation we'll be using often for all these calculations, y, different values of y. Now tau, the shear stress, is equal to mu into du by dy. Mu is given directly. We should be able to calculate du by dy. Now what is du by dy? Differentiation of u with respect to y. This is a function of y. So it will be a constant 5. Sine becomes cos of 5 pi y, and differentiation of inner function. So it will be 5 pi. So overall it becomes 25 pi cos 5 pi y, and this is mu. If you simplify it, it will be 12.5 pi cos 5 pi y. That is what the shear stress in terms of y means. This expression is equal to tau, the shear stress, as y varies. The first data, that is y equal to 0, means nearer to the surface y is not much or almost 0. Then if I substitute y equal to 0 in this equation, you will get that it is 39.27 Newton per meter square. So that is what is the shear stress at the surface. Now if y is 0.05, means slightly away, obviously what you should expect is, if du by dy is decreasing as you go away from the y, this value of shear stress has to get reduced. Let us see what happens. So for y equal to 0.05, if I calculate after substitution of y, it is becoming 27.76. We have observed it rightly. This is much more nearer to the surface, and then as you move away, the shear stress is reducing, right? Even further, that is y equal to 0.1. If you calculate that, the shear stress is reduced to 0, means at 0.1 distance, at a distance of 0.1, the velocity is no different, it is remaining the same. That's why if there is no du, it is 0. So as it becomes 0, the shear stress becomes 0. So that is how the shear stress changes from nearer to the surface as you go away from the stationary nearer to the surface into the fluid, moving fluid. The shear stress becomes less and less. Nearer to the surface, shear stress will be larger. That is what is kind of observation that you can do. We'll go to the next one. So here, power lost in viscous resistance during rotation of a rod in a sleeve. So here there is a sleeve, right, 50 centimeter sleeve, and this rod is rotating into that, right. The power lost will be given by directly an equation like this, right. We'll see the problem now so that we can note down all the details. Now a cylindrical shaft 90 mm in diameter is shown, 90 mm in diameter, rotates about vertical axis. It is rotating about a vertical axis is shown here. So here that is the point which will be showing you an axis. So it is rotating in anti-clockwise manner like that. 90 mm diameter rotates about a vertical axis inside a fixed cylindrical tube of length 50 centimeter. So here the tube is shown and there is a gap here. When you cut a section, what you see here is this particular edge of the tube, and then the length of the tube they have given 50 centimeters. So inside of this 50 centimeter tube there is a rod and 95 mm in internal diameter. So 95, the tube has got 95 as the internal diameter. The rod is 90 mm, means there is a free space available, right. So total difference is 5, in the sense here this thickness will be 2.5 mm, this will be 2.5 mm. Okay, if the space between the tube and the shaft is filled by a lubricant of dynamic viscosity 2.0 poise, so dynamic viscosity is given, mu is given 2 poise. If you convert that into Pascal seconds, it will be 2 by 10 Pascal seconds or Newton second per meter square. Determine the power required to overcome viscous resistance when the shaft is rotated at a speed of 240 rpm. So n is given revolutions per minute. The diameter d, inside diameter d, is given 90 into 10 raised to minus 3 meters, because 90 is given in millimeters, will be operating in Newton second meters. That's why this has to be converted into meter. So I have multiplied by 10 raised to minus 3 so that it can be put as meters. Then length is given 50 centimeter. If you look at this, so again this has to be converted into meters, so divide by 100 so that it becomes in meters. Now 95, 90, this thickness of the oil film, here it becomes, the clearance becomes 2.5 mm. Again, the if I represent that as T, the T will be equal to 2.5 into 10 raised to minus 3 meters. Now if you put all this information in a direct equation, power required to rotate the shaft, power lost during rotation, whatever terminology you can use. So P is equal to pi cube d cube n square mu L divided by 3600 T. T is this TRH. It is one and the same, right? In this case, they have written it as H, but actually what I mean by this is a T, right? So you can read the problem also as T, the thickness of the oil film around shaft. So now P comes out to be 14.466 Newton meter per second, or watts it will be. Okay, we'll see the details. This is rotating shaft shown here. Anyway, here how using fundamentals, if you want to solve the same problem, you can just see here what is done is phi, circumferential velocity, means if you have a velocity here, this is rotating. So if you want to calculate surface velocity tangential to this, so that velocity becomes, if I try to draw at this particular point, the velocity will be like this. Or if you want to draw it here, it will be tangential like that. Or if you want to draw it here, it will be tangential in the sense vertically downwards. This velocity phi is r omega, and omega is 2 pi n by 60, r is r. So if you substitute in proper units, it is becoming 1.131 meter per second. So this velocity circumferentially, it is so much. Now if you can think here there is a oil film, right? So this part, if I exaggerate, there is a rod, there is a tube, all this is filled up with oil, and here there is a velocity. Now this is stationary, so because of that what happens is the velocity distribution becomes like that, and this we are considering linear. What I mean is, if you come away from the rod, the velocity is decreasing and it becomes ultimately 0. This is a linear velocity distribution. Because of that, we choose v by t or v by h as du by dr, right? So that is the reason. Because it is a linear velocity distribution, it can be taken as du by dr can be taken as simply the v divided by this h, thickness of the oil film. Anyway, here clearance h is calculated. It is easy to understand. 95 minus 90 divided by 2.5 mm, and v by h, velocity gradient, is calculated 1.131 meter per Second is the velocity. The thickness of the oil film is 2.5 into 10 raised to minus 3 meters, and mu is given to be 0.2 Pascal seconds, because it is given to poise, that is 0.2 Pascal second. Further, here shear stress tau is equal to mu into du by dy or dr. In this case it is a radius, so it comes out to be 90.48 pascals. Now shear force is the shear stress multiplied by area, the area of contact inside the cylindrical surface, because it is a cylinder, right? Inside a tube of length L, and then a radius R. So what is the surface area that it is in contact? It will be 2 pi r, circumferential length, multiplied by L. So circumferential area of a cylinder becomes 2 pi RL. That's why this formula. Now substitute, you'll be getting the force, the viscous force, as 12.791. The force is given by this. Now the torque will be that force multiplied by the distance, because this force will be acting all along the periphery. This is Fs, or viscous force. They have shown it as Fs. Now this is acting at a radial distance of r. Now what is the torque that is produced because of this, or what is the moment that is produced? That is what is shown here. So the force multiplied by this radial distance will be equal to 0.6756 Newton meters. This is torque. Now what is power required? Power is given by 2 pi n T by 60. So substituting all the values, we end up with 14.5 watts. You have seen in a couple of slides earlier that there was a direct formula, and that is much easier rather than going into all these details, but it is better always. You should know how to arrive at this particular value by using fundamentals also. Go to the next problem. So here there is a situation, a metal plate of size 0.6 by 0.6 and 1 mm thick and weighing 25 newtons is to be lifted up edgewise with a uniform velocity of 0.2 meter per second in the gap between two flat surfaces. Okay, here I have shown that plate. The same plate is being shown over here. This thickness they have given that it is 1 mm. This thickness is 1 mm, and then whatever surface that will be seen here on the side is 0.6 by 0.6. So 0.6 is this way, 0.6 is this way. So the surface area which is in contact with the oil, will be equal to 0.6 by 0.6. So area of contact with the fluid becomes 0.36 meters square. Here the viscous force will be acting in the opposite direction, right? Now the distance between the two plates, the plate is inside the middle of gap of width 2 mm, and the gap contains oil of relative density 0.85 and viscosity 1.6 poise, right? So the gap is 2 mm. It is not meter, it has to be millimeter, right? 2 mm. 1 m is missing, so this thickness is 1 millimeter. So what happens is this thickness, whatever leftover thickness over here and over here is there, that can be calculated, which will be 2 divided by 2, right? So that becomes 1. 1 is to be distributed over here and here, so it will be 0.5, because 2 minus 1 is 1. 1 divided by 2 becomes 0.5, 0.5, right? So the thickness of the oil film becomes, here I have shown that it is oil film thickness is 0.5 mm. Okay. Okay. Now the idea or the concept is calculate vertical force required to do this job. Now this is moving, right? So the plate is moving now up with a constant velocity. Velocity is constant, and then you remember the a point that when the object is moving, the with a constant velocity, the resultant force is equal to 0. So here the forces are the forces which are acting on the object. If you look at free body diagram, the force Ft is being pulling it up, Ft, and the two viscous forces on edge surfaces, one surface over here, one surface there. There are two viscous forces. If Fv is viscous force on one side, minus the weight of the object is equal to 0. So this is all summation of vertical forces. You have seen that in horizontal system there is no weight coming into picture. Here the weight also comes into picture because it is vertical. So from this we can calculate whatever required quantity. Now in this, how much is Ft? That is an unknown. Fv we should know. W they have given, right? The weight of the object is given to be 25 newtons. Fv I have to calculate. Now Fv, the viscous force, is given by shear stress multiplied by area. Area is also calculated, right? This mu is given to be 1.6 poise divided by 10 gives you Pascal seconds. Du by dy can be taken as V by T. The V, 0.2 meter per second, the velocity, and divided by this thickness of the oil film is 0.5 mm converted to meters, multiplied by area. The area is 0.36. So one viscous force on one side becomes 23.04. Now coming back to this equation, substituting will yield towing force. The force to tow the plate up will be equal to 71.08 newtons. That's an interesting problem. Hope you'll like that. Next one. Here I have shown the viscous force. There are two viscous forces, obviously one on each side. Okay. So there is a cylindrical body. Next problem. 90 mm in diameter. 90 mm in diameter. So this length is 90 mm. Sorry, 90 mm in diameter. So this is 90. I'll draw that. So diameter in the sense here, this one. It is written over here, but it's hiding behind the object anyway. This is 90, and 500 is this way. This is shown 500 millimeter converted to meters, and of weight 15 newtons. So the weight is acting vertically downwards. Slides vertically down a 92 mm cylindrical sleeve. Okay, there is a sleeve having a length, right? What is the length? The space, anyway, whatever, 500 millimeter. No, 500 millimeter is the cylindrical body, and then it is moving continuously inside this tube, right? It is, the tube is totally continuous, right? There is a gap between tube and the object, and that calculation I have done because tube inner diameter is given to be 92, right? And minus 90, that is the diameter of the object, divided by 2 gives you one thickness. Another thickness will be there, so it will be 1 mm. So this is 1 mm and this is also 1 mm. So 1 mm converted to meters is 1 into 10 raised to minus 3 meters. Okay, now we'll read it further. The space between the body and the sleeve, that is this object, right? Body and the sleeve, which is there all along, is filled with oil. Now determine the dynamic viscosity of the oil needed to restrict the velocity of the fall of the cylindrical body to 5 centimeter per second. Assume linear variation of velocity across the gap. This I have explained you in the earlier slide. Now what is important is the velocity with which the object is moving downwards because of its weight is said to be constant, right? It has to be restricted to the velocity of fall of 5 centimeter per second. Again, the point is, because the velocity is constant, we can say that acceleration is 0. That is the point again. And because acceleration is 0, sigma fy is equal to 0. But what are the forces which are acting on this? There is a weight W and there is a viscous force which is acting all along this cylindrical surface, right? So Fv is upwards, that's why I have taken it as plus minus W equal to 0. Only one Fv I have shown, but it is not acting only on this side, it is acting all along the cylindrical surface, right? So Fv, when we calculate, we should see that it is shear stress multiplied by the area, and this area is the cylindrical surface area which is in contact. Means cylindrical surface area, you know that it is this way. It is when it is opened up, it will be having pi d or 2 pi r multiplied by h or height. So that gives you all this cylindrical surface area all around. So it is pi into d multiplied by L. L is 0.5 meters. So this is pi dl. Okay, I'll try to write it as, so surface area becomes, cylindrical surface area becomes pi dl. Mu is how much is the mu given? Okay, mu is to be calculated, that is the unknown. Du by dy, du is 0.05 because 5 centimeter it is given, divided by 100, right? 0.05 meter per second. So this unit is anyway meter per second, divided by dy, that is thickness, is 1 mm. So 1 mm is substituted as 1 into 10 raised to minus 3 meters. So overall, if you look at this, right, what is the value of mu if you simplify, because the viscous force or the is given by this, and this is equal to W, that is 15 newtons. So this has to be equal to 15. So only unknown in this equation is mu, the viscosity. So mu is equal to 0.212 Newton second per meter square. So this is because everywhere we have used Newton and meters, obviously units for mu becomes Newton second per meter square, 0.212 Pascal second. If you want this in poise, you have to multiply by 10, so it becomes 2.12 poise. Okay, so that's how the cylinder is falling down, and the viscous force all around the cylinder will be acting that way. Okay, thank you. We'll stop here.